the group of people there. So maybe I'll just go ahead and kick things off and welcome everybody to the last Fellows Seminar of 2023. Hard to believe it's December already, but we're already looking at the new year with another crop of Fellows seminars to begin in January. Today's talk is going to be given by Maurizio Barbieri and Stefania Franchini. I hope that I pronounced that okay, who are going to be talking on isotope-based early warning models, an example of high-resolution site characterization. And this is something that touches on an area I'm very interested in, that of using stable isotopes to evaluate remediation in groundwater. So without much ado, I'll hand it over to our speakers. So take it away.
Okay. I hope that you can view our screen. Okay, all okay. Thanks. Good afternoon to everybody. My name is Maurizio Barbieri. I'm a professor of geochemistry at Sapienza University of Rome. And with me is Stefania Franchini, that is a young researcher in geochemistry at another department, but at the same faculty of engineering of Sapienza of Rome. And this evening we want to approach an isotope-based early warning model that is an example of an high-resolution site characterization, because we know that one of the serious environmental threats is represented by groundwater contamination in areas subject to anthropogenic activity. But during the last decades, one of the most important approach is the isotope-based approach that can give us main information, especially to trace the water pollution and the environmental problems related with these threats. I want to leave the presentation to Stefania, and I hope that this presentation will be an important example for our society about the environmental problems and the new possible approach to this thematic.
Okay. Good afternoon to everyone. Okay.
Yes, just a moment.
Okay.
Okay.
Nowadays, one of the serious environmental threats is represented by groundwater contamination in areas subject to anthropogenic activity. Water is regarded as one of the most important natural resources. Indeed, water resource and water quality are important and indispensable for human survival and the ecological environment. Okay. Solid waste is increasing globally because of increasing population and living standard. Thus, proper treatment to solid waste is critically important to societal development. Among waste management options, landfilling is considered a simple and cost-effective treatment method, and often acts as the last destination for the waste after appropriate treatment. Landfill leachate can be characterized as a soluble organic and mineral compounds generated when water infiltrates the refuse layers, extract contaminants, and trigger a complex interplay between the hydrogeological and biogeochemical reaction. This interaction act has a mass transfer mechanism for producing moisture content sufficiently high to initiate a liquid flow induced by gravitational force. Landfill leachate is one of the most complex waste streams to manage because it contains a wide range of organic and inorganic compounds, including nutrients, chloride organics, inorganic acids, inorganic salts, and heavy metal. The leachate composition in terms of chemical and microbiological matters varies among different landfill types and depend on many factors such as, for example, the characteristic and the composition of the solid waste, the environmental condition, the landfill operation mode, and the decomposition mechanism of the organic matter. Waste decomposition process is by bacteria involves in 4 stages: aerobic stage, hydrolysis and fermentation stage, anaerobic acetogenic stage, and anaerobic methanogenic stage. The first phase of landfill decomposition consists of the aerobic oxidated of organic matter and the consumption of free oxygen in the residues. This phase is followed by reactions such as oxidation, hydrolysis, and anaerobic acidification that results in the accumulation of CO2 and organic acids and decrease the pH of the medium. With the continuum of anaerobic degradation, methanogenesis becomes the predominant phase in the landfill, where a decrease in acetic acid and other organic acid is associated with the increased pH and methane production during the development of this phase. Since percolation of the leachate can compromise the quality of water, the assessment of the contamination of surface and groundwater surrounding a landfill is one of the main environmental concerns. Thus, this site needs environmental monitoring program capable to identifying the influence of the leachate in water resource adjacent to the landfills area. Conventional monitoring programs typically involve periodic sampling of surface and groundwater for the determination of chemical parameters, such as, for example, quantity of inorganic ions, heavy metals, alkalinity, pH, chemical oxygen demand, and so on. Sometimes using chemical analysis alone and unvaried characteristics is insufficient to explain the spatial and the temporal variation of the contamination load and its concentration in water. So the use of additional tools such as stable isotope can provide additional information. Variation in groundwater chemical abundance and isotopic composition can be used as a natural tracer to determine sources, pathways, and timescales of environmental processes. Deuterium and oxygen-18 traditional isotope ration are recognizable tracer related to the water cycle and have been widely used in hydrology. The presence of deuterium and the oxygen-18 stable isotope in water cycle is conditioned by meteorological processes, which give a typical footprint that is useful also for groundwater contamination characterization. These isotopes are generally defined as tracers, as the conservative tracer, as they retain their features over the full path of the groundwater. While deuterium and oxygen-18 generally correlated with the temperature at the middle to high latitudes, the deuterium excess is associated with the physical condition of the oceanic source area of the precipitation. The D-excess can be used to identify processing occurring under non-equilibrium condition. On a global average, the general relationship between delta O18 and deuterium for natural precipitation water and at a particular site over time is linear and expressed by the global meteoric water line. So del D equal 8 delta O18 plus 10 per mil. Deviation from the global meteoric water line is defined by a local meteoric water line, which can be expressed by the deuterium excess, like del D minus 8 del 18 delta O18. In the Eastern Mediterranean, the excess values is higher than 10 because evaporation processes of the sea surface occur in low humidity air mass of continental origin. So the Mediterranean meteoric water line has expressed the oxygen-hydrogen isotope relationship like del D equal 8 del O18 plus 22 per mil. This stable isotope in landfill, such as the del C13, deuterium and del O18, are influenced by the processes within municipal solid waste landfills, mainly on the methanogenesis phase of the landfill. Landfill gases, so CO2 and CH4, and the landfill-aged product, water and anorganic carbon, have a characteristic isotope in terms of deuterium and del O18 respected to the surrounding environment. Methanogenesis is the process that determines the production of methane and carbon dioxide in a landfill by some microorganism known as methanogens. Several studies have shown that the methanogenesis phase is the case of the enrichment of the dissolved inorganic carbon and hydrogen stable isotope in the leachate. Methanogenesis can cause a deuterium increase because the bacteria use preferentially the lighter isotope, hydrogen, and due to the methane production, thus the remaining hydrogen is enriched in deuterium, that is the higher isotope, with producing a proportional increase in oxygen 18. This process seems to increase the D excess without a proportional increase in oxygen 18. Due to methane production, the deuterium ration can be located outside the traditional range associated with natural waters of direct meteoric origin meteoric water line, shifting to positive range. So the deuterium enrichment is groundwater surrounding landfill sites can be used to indicate leachate migration from landfill to groundwater and other activity near the study area. The del D of landfill leachate is strongly enriched in deuterium by approximately 30 per mil to nearly 60 per mil relative to local average precipitation values. This deuterium enrichment is undetectable due to the extensive production of microbial methane with the limited reservoir of a landfill. Another factor that can determine the variation of the deuterium content in the leachate produced by landfills is the alternation between dry and wet season. On the contrary, it has also been observed that methanogenesis does not affect the oxygen 18 isotope composition. Study highlights that oxygen 18 isotopic composition variation in leachate are due to seasonal precipitation variation, reflecting a rapid movement of water through the peel with minimal storage in the west. As isotope analysis of deuterium and oxygen 18 can be carried out monthly at an affordable cost, the proposed method can be defined as early warning as it allows prompt intervention in the case of specific values of the isotope determination. Early warning system represents a relevant choice with the landfill risk management framework, primarily when structural measurement cannot fully guarantee the safety of the area of interest for contamination phenomena. This webinar aimed to show the effectiveness of applying deuterium as a tracer and of the illicit present in groundwater near municipal solid waste landfills when a significant amount of organic matter is present. Here it is shown that the illicit present in groundwater can influence the deuterium ration without determining an DELT-18 enrichment, and how an early warning model can be proposed based on the assessment of the deuterium excess variation, which can occur after precipitation infiltration inside the subsoil. In particular, we want to highlight how innovative monitoring tools that reach high sampling frequencies with low-cost producer analysis represent a significant improvement likened to traditional approaches. Now we show the application of deuterium and oxygenating isotope for treating municipal solid waste landfill contamination of groundwater into Italian case history. For a suitable assessment, the isotopic composition data for both history cases are compared with the main meteoric water line, so global meteoric water line, Mediterranean meteoric water line, but also with local meteoric water line for southern Italy described by this equation, and local meteoric water line for central Italy described by this equation. The deviation from global meteoric water line and the Mediterranean meteoric water line show alteration phenomena due to processes occurring in the soil, mixing with marine water of ancient or recent origin or contamination with leaching from soil to groundwater. In particular, the variation by meteoric line highlights the mixing phenomena of groundwater with leachate coming from landfills of municipal solid waste consisting of a significant organic part. Okay, now case history 1 refers to a plant in the Cagliari province in Sardinia region, while case history 2 deals with a plant in the Perugia province in Umbria region. In both study area, there are in operation landfill used for storage of municipal solid waste with organic component of municipal solid waste was not negligible. For case history 1, the Capocaccia gas station is identified located to the northwest of the plant, while for case history 2, the Piandelelmo gas station is identified located to the northeast of the plant. For case history 1, we highlight the deuterium anomalous values for the P12-bis sample, like minus 18 per mil, located downstream of slot 2, used for municipal solid waste storage. The delta-rich enrichment confirms an interaction of the leachate from slot 2 with groundwater, so a phenomenon that therefore an index of contamination processes. This behavior is also confirmed by the concentration values of some analytes, such as iron, manganese, and nickel, with values over legislative degree 152.06 threshold, validating the hypothesis of pollution for the P12-bis groundwater sample. Point P12-bis has the values of delta-018 equal to minus 6.003 per mil, very close to the results of the leachate point 2. Also in the case history 2, we highlight anomalous deuterium values in AD16 groundwater sample, like minus 24 per mil, and AD16 point appears to be located near the tank 1, PA1, which is for leaching collecting. The deuterium enrichment indicates a pollution phenomenon caused by the interaction between leachate and groundwater. This phenomenon is also confirmed also in this case by the concentration of some analytes such as iron, manganese, and nickel with values over legislative degree. 152.06 threshold. So the groundwater sample AD16 had a delta O18 values equal to minus 7.5 per mil, very close to results of point PA1. However, for both cases, the Deuterium enrichment does not lead to a following del O18 variation, confirming that the methanogenesis phenomena do not influence of oxygen isotope content. Furthermore, a statistical approach was applied for both case history using the Pearson matrix to study correlation between deuterium and del O18 isotope and concentration of iron, manganese, and nickel. The Pearson matrix performed for both case history confirm a high relationship between deuterium and iron, manganese, and nickel concentration. On the contrary, no enrichment are highlighted regarding a relationship between that O18 and the iron, manganese, and nickel concentration, as that O18 is not involved in such processes. In conclusion, the case history proves how deuterium enrichment determines a significant shift of the groundwater sample from the reference meteoric lines. This processing confirmed that the methanogenesis phenomena cause a deuterium enrichment due to bacteria using the lighter isotope hydrogen without generating variation for the oxygenating isotope. This case history confirmed that the deuterium enrichment is a valid tracer to identify contamination processes between the leachate from municipal solid waste landfill and groundwater. In conclusion, the present comparison between deuterium enrichment and other metal let us outline that when there is a deuterium enrichment and one metal high concentration values, these latter values are due to the contamination processes and cannot be repaired to a natural background level. For case history 2, we propose an original procedures to apply an isotope-based early monitoring model for monitoring the potential mixing phenomena between groundwater and leachate from a municipal solid waste with a significant component, organic component. The proposed procedures determines an F-index given by the relation between the d-axis for the sample and the d-axis reference value. Since the latitude influence the d-axis trend for the case study, the local meteoric water line to the Pian-Dell'Elmo station is considered the reference value of the d-axis, whose intercept values is equal to plus 18.15 per mil. Based on the values assumed by the F-index, the model proposed 3 zones with diverse warning levels. So F-index values lower than 1 indicate a buffer zone. F-index values between 1 and 1.1 show a warning zone. And F-index values higher than 1.1 reveal an alarm zone, confirming contamination phenomena between groundwater and leachate. The values 1.1 indicate an increase of more than 10% in the sample's d-axis compared to the reference d-axis. For sample were analyzed in 4 different months, representing a whole monitoring year, hydrological year. The D16 sample present an enrichment of deuterium for all 4 monitoring surveys, with values ranging from a minimum of minus 28.20 per mil in April to a maximum of minus 22.74 per mil in January, therefore presenting a higher F-index to 1.1 for all monitoring surveys, with values between 1.96 and 2.072. Sample AD13 show an enrichment of deuterium in April with a values of minus 37.6 per mil, resulting in AF index of 1.36. At the same time, the sample AD68 and AD73 show deuterium values equal to minus 41.18 per mil and minus 44.10 per mil respectively in April. Their results showing an F index equal to 1.21 and 1.22 respectively. The leachate sample PA1 and PA2 taken as the end member of possible mixing processes have F index values that are all within the alarm zone, and also AD16 sample show values of F index at beginning with the alarm zone, confirming the contamination phenomena of draining water by leachate. In April, the D73 sample show an F index value in alarm zone. On the contrary, there are not anomalies in July and October. At the same time, the D73 and AD68 sample present an F index values in the warning zone. The occurring values of the AD13, AD73, and AD68 sample resulting from the April monitoring surveys could be due to a seasonal anomaly. Therefore, monthly cumulative rainfall and monthly average temperature were also analyzed to assess the seasonality influence. April 2020 was a month characterized by large precipitation and moderate average temperatures, and this process influenced the deuterium enrichment in sample AD13, AD73, and AD68, which show values of F measured higher than 1.1 for the AD13 sample, and values in range 1 and 1.1 for the AD73 and AD68 samples. However, for July and October 2020, the F lower than 1 for all three samples, thus confirming a seasonal anomaly. On the contrary, the sample does not seem to be affected by seasonality. In fact, it shows F higher than 1.1 in all monitoring surveys. Seasonality is a parameter to consider in F index assessment, as it can affect the deuterium enrichment and the D access in groundwater sample. In conclusion, according to procedure of this proposed model, the determination and monitoring of F index can be a value tool to assess and manage possible mixing phenomena between groundwater and leachate from municipal solid waste landfills. This proposed isotope-based early-warning model is still in the first phase, as it would be better to consider a meteoric waterline to reverse to the study area for the F index determination, as the d-axis is highly affected by latitude trend. However, the Mediterranean meteoric waterline has been considered as a reference in the lake of other information and as a cautionary guide. Another innovative method that we would like to present today concerns industrial sites with high risk of groundwater pollution from heavy metal. Chromium is one of the heavy metal considered dangerous for human. And a slight increase in the level of chromium-6 causes the environmental and health problem. In contaminated state, the effectiveness of remediation measurement is increasing, depend on previous high resolution site characterization results. However, in many industrial sites with high pollution risk related to groundwater, hydrogeological models are often based on only the stratigraphy results of geological drilling related to the groundwater monitoring network design. Even if suitable for modeling groundwater flow, this approach does not fit when contaminate back diffusion from low permeability lands and layers and occurs at different points within high permeability aquifers. Throughout the hydrogeological cycle, more than 99% of pollutions are stored in sediments, aquatic systems, leading sink and carried off contaminants. In particular, the absorption capacity of sediment increases with the decrease in particle size. High resolution local stratigraphy model can be obtained by coupling stratigraphy data with a specific measurement in the monitoring as well, like such as a natural gamma radioactivity log. The most radioactivity elements in sedimentary formation are the isotope uranium-238 and thorium-232, and the isotope potassium 14. The concentration of uranium and thorium are similar in most sedimentary formation. In contrast, the potassium concentration divide them into two groups: the clay mineral with relative high concentration, and the rest with a insignificant proportion. Therefore, these characteristics allow us to determine soil clay content by gamma ray log. The log of natural gamma radioactivity is beneficial for lattice stratigraphic reconstruction by discriminating clay levels, so impermeable, from sandy gravel levels, so permeable. In the study site located in Benevento in Campania region, groundwater pollution by chromium-6 was recorded. During groundwater monitoring chromium-6, various decreases in all monitoring wells except PZ8. Indeed, in PZ8, there was a significant increase in the concentration of chromium-6, followed by a gradual decrease. Considering that chromium-6 has not been part of the plant production processes for years, the temporary increase in chromium-6 concentration in PZ8 cannot be due to primary sources of contamination, but to the activation of secondary sources. So we compared the data of chromium-6 concentration recorded in PZ8 with the rainfall and hydrometric data of the monitoring station closest to the study area. In the period study, there was an increase in precipitation corresponding to an increase in hydrometric level, precisely in the same period in which the concentration of chromium-6 recorded by PZ8 increased. More in detail, it is possible to observe how the concentration trend of chromium-6 decreases suddenly, just like the rains. The fact that chromium-6 follows the rains trend and not the hydrometric level indicates that this is a local pollution phenomenon. Therefore, it is not a source of pollution transported from far away from the rivers in the area, but it can be assumed that there is a hypothetical source of pollution not far from the site. The gamma radioactivity core was carried out at different depth in 3 select piezometer, including the PZ8. A statistical data evaluation led to the calculation of sigma plus and sigma minus, which are given by the sum and the difference between mean and standard deviation respectively. The peak highlights beyond the sigma plus values represent the level with higher concentration of radioactivity elements, indicating the presence of levels of levels or lands with a higher clay concentration, so impermeable level, while the peaks light below the sigma minus values represent represent the level or length with lower concentration of radioactivity elements, indicating more sandy gravels levels, so permeable levels. The study area, in conclusion, the study area has a stratification with different permeability, with more permeable levels consisting of sandy gravel deposits and less permeable layers consisting of clay levels. Water passes and filters the most permeable horizons more quickly, but during the increase in hydraulic load due to increase in rainfall, water also involved the less permeable horizons. Thanks the PZ8 was continuously pumped, it has drawn towards itself the polluted water, meaning that the clay levels identified have captured the pollutant. So in area affected by pollution, a year of higher rain induce a rise in the piezometric level that involves the movement of pollutants nestled in less permeable horizon that are engaged during higher hydraulic head. This explains why in areas where contamination seems to be resolved, there is suddenly a high pollution concentration, even though it is not longer present in the production process of the plants. Therefore, this is simply a release of contaminants still present in the area and not a new contamination phenomenon. The increase in piezometric level and therefore the variation in the interstitial pressure have favored the release of chromium-6 that has settled in a clay lens and that once put in motion follow a preferential way that goes through the PSA8. In this context, the use of gamma ray in combination with the analysis of the pluviometric and hydrometric data, and together with the time series of concentration of metal, help to understand the phenomenon that induce the subsequent release of pollutant despite the following of all safety measurements in the area subject to pollution. This makes it possible to reduce the remediation costs and times, as it is possible to identify the area in which it is necessary to deepen groundwater management. Thank you for the attention.
Great, thank you very much, Stefania. We have time for questions. What I would maybe ask you to do is to put any questions in the chat, and then we can kind of work our way through that. Or if anyone, alternatively, you can just raise your hand and I'll take your question that way. Not seeing any questions. I have one of my own, and I didn't quite pick it up on the first presentation regarding the stable isotopes and the deuterium, but what distance were the monitoring wells from the assumed source of the leachate?
Okay, the distance from...
I know you did show a map, but I didn't quite catch the...
We don't have a map, but the location of the... Okay, here. You... But I give you the...
Okay.
The location of the monitoring wells are near the plant site, is inside the plant and in the area surrounding the plants.
Yes.
Okay.
In all the case study.
The near this station is to identify like the nearest of the plant of landfills.
Okay, so in the order of, you know, hundreds of meters or
Yes,
kilometers?
no, 100 meters.
Right. Okay.
Okay.
Great. So would you expect that the deuterium signature, the elevated deuterium ratio would be detectable before some of the metals in the plume?
We expect that this is correct, but the very different approach is related that in all our previous studies, we approach only with trace metals and with iron and manganese concentration coming from the methanogenic processes. And in this case, we want to approach with the deuterium excess to verify if methanogenesis phenomenon can influence these isotopes approach, because we have many data and many Italian cases about this phenomenon of contamination in plants used for landfill, and it's important to have another more quickly and more expensive and not so expensive methods to approach. But I think that is very important and fundamental for this approach to have a very big series of data coming from the chemical groundwater data and soil data, because only with a very big database we can use this approach, and we can have a interaction with isotope approach and the trace metals approach that are very important and useful and most used in the last decades.
Great, thank you. All right, we have a question online from Alex Stewart. What is the rationale for choosing 1.1 as the F boundary between warning and pollution? Why not use 1.15 or something else?
Yes, the cabin sheet.
Okay. Yes, just a second. Okay.
Okay.
So, we chose the values of 1.1 because they indicate an increase of more than 10% in the sample the excess, that there is the values the humidity of the area in this part of the world.
This is a choice, but we try to use 1.1 because it indicates an increase of more than 10% in the samples of the deuterium excess compared to the reference. But this is the first approach, okay? And we can use another one if the data set indicates other information. 1.1 indicates a good it was in agreement with the trace elements concentration variation.
Thank you. Have you done any sensitivity analysis looking at moving the 10% boundary? Have you recalculated, say, at 1.05 and 1.15 to see what happens?
Okay. We can try to use in the next approach, because we have another plans that we are studying, and we want to try to a different approach for the F index. Yes, of course, especially with the temperature data.
Right. Thank you. Am I allowed another question, Keith?
You are indeed, Alex.
Let me remember this one. It was in the third section with the graph of the groundwater, the precipitation, and the chromium peak.
Yeah.
It looked to me, no, the slide before that one.
Yes, this one.
Yeah.
Yeah. I can't see that the chromium follows the rainfall rather than the hydrometric level on that.
Yes, we have only an incrementation in level in the chromium concentration that can reflect the concentration, the amount in the rainfall and the hydrometric levels after 10 days, okay, with a shift of 10 days. In this case, we don't have any information coming from the plants that used chromium-6 as toxic elements for the industrial processes, okay? But the very particularly of this site was that that was a clear indication or a clear indication that the chromium follow the rainfall and the hydrometric level after 10 days. So we can try to go to this hypothesis that there is a pollution in an area surrounding the plants that in particular rainfall and hydrometric condition we will move to the plants, but not coming from every period during the year, but only in some period when the rainfall or the hydrometric levels become more influenced.
You've got a nice rainfall peak in September.
Yeah.
But no increase in chromium.
Yes, it's
why not there?
Our hypothesis is that the level of the rainfall and the hydrometric level was not so high to produce a release of the chromium coming from these clay levels.
Do you think the intensity of the rain might matter?
Yeah. Yes. This is
Right.
the hypothesis.
Or could it be, just looking at the graph, could it be a combination of high groundwater levels and heavy rainfall?
Okay. See, we can try to there is a combination. Yes, I think that there is a combination because in this case we don't have any chromium information, so chromium excess. Okay.
Yeah, you have a low groundfall.
Yes.
So not. Yes. Okay. It's interesting. I'm intrigued.
Yes.
Yeah. Well, thank you for presenting.
Yes, this is some example coming from a new approach to to improve our information about all the tracers that we can use as environmental tracers.
Keith, is there any data back in Glasgow from the chromium site under the motorway?
Okay. Yeah, I was just thinking about that. We have a very severe issue with chromium-6 contamination in parts of the east end of Glasgow. I don't know if there is any borehole data, but there is there is a stream that's been culverted that drains the area where the worst contamination was, and it does show significant variation in chromium content. I mean, it's so bad that you don't need a spectrometer to calculate how much chromium is in the water. You just need to look at the degree of yellow-green in the water. And it's likely that the source of that is chromium ore processing residue, copper, which was dumped all over the city. But although it's been supposedly remediated, there's probably pockets where, it just wasn't identified, but also conceivably that it's been, the chromium is retained in some of the clay-rich sediments of the area.
Okay.
Yeah.
Interesting.
Thank you.
The other one. That time together. So you can see all those time we.
So, Emmanuel, do you have a question or any further questions? No? Okay, well, I'd like to thank you both for a very interesting and stimulating talk. Certainly of great interest to us here in Glasgow. And finally, I'd just like to ask you all to show your appreciation to our speakers.
Okay, many thanks to this opportunity that is very interesting for us to share with you and with the society. Okay, thanks. Great,
and thanks again. So look out in your inbox for news of the next batch of seminars, which will be starting again in January.
Okay, thanks.
Great.
Okay.
Thanks again. Bye-bye.